We're the last one for tonight.
Yes.
So we're about to talk about the Impossible Project. This is a project that required multiple science agencies and also a Department of Defense and Intelligence agency. You can't hear us? Is this closer? Okay. And so what we did was to use high resolution sub-meter commercial imagery. So this is imagery with a resolution of about this much, collected over a period of about 5 years to create an elevation model that's publicly available for the Arctic.
From about probably 2 million scenes.
With millions of scenes of imagery. So next slide. And so we used imagery, in this case from 6 satellites that were licensed to the US government by the National Geospatial-Intelligence Agency. They're basically orbiting telescopes, but instead of something like Hubble that's pointed out, these are pointed down. It's pretty much the same thing. And so over a period of about 4 years, we took this imagery that was collected 45 seconds apart, 10 gigabyte strips, and we moved about 100 terabytes of this imagery into a place where, 100 terabytes, a petabyte of imagery into computers that allowed us to process this into high resolution elevation models. Next slide. One of the most amazing things about this satellite constellation is their very high inclination for orbit. They're going basically from 84 or 85 all the way around. So at the poles, we can see any one location in the Arctic or the Antarctic as frequently as about 15 times a day. And so what was delivered in September of last year was this. This is a 2-meter posting. So basically the height of a tall man elevation model. Publicly available, no copyright at all. And it includes an area that's about 20 million square kilometers. But to be able to make up this 20 million square kilometers, it took imagery of over 200 million square kilometers to make this. And so what you're seeing here is extremely good elevation for Greenland and Siberia. We have poorer elevation here that's soon to be corrected, but this is what's now available public. Next slide, please. The first delivery of this information was Alaska. And so in 2015, President Obama proposed this project, and we had 12 months to not only create Alaska from basically raw imagery, but we had 12 months to create the factory that created Alaska. And so what we have here is the next generation of Alaska that will be delivered at 2-meter resolution in about August or September of next year. Next slide. The North Slope. We've created the elevation for the North Slope no less than 6 times. And so unlike elevation that we have in the lower 48, where you only have one collection every 5 years, every 10 years, or maybe not at all, we have the North Slope once a year. And that allows an investigator to go in and look at thermal karst collapse, to look at deforestation, to look at tundra fires.
So for vegetation, this is remarkable because you can look at the volume of vegetation, because these are 3-dimensional images that are being produced. It also enables you to look at ice stream velocities and many elements of the cryosphere. And you can do this year after year after year, at the spatial resolution of 2 meters by 2 meters in the XY, and a vertical accuracy on the order of 15 centimeters. So this is remarkable for our study of polar regions in the Arctic and in the Antarctic.
Next slide. And so now we get in where the rubber meets the road. Because these are polar orbiting satellites, because we don't need fixed wing logistics to bring LiDAR in, we can see anywhere all the time. And in this case, what we're looking at is Yakutsk along the Lena River in Siberia. And so this is an auto-generated 2-meter posting elevation model of a braided stream and one of the most highly populated areas in Siberia. You can see in this elevation road cuts, you can see deforestation and just timber harvesting, you can see airfields, and of course you can see the buildings themselves. Next slide, please. We're again independent of geography. This is the Kernalsky Gulf in Kamchatka. So actually north is this direction. And you just have volcano after volcano after volcano after volcano. And because these satellites are not just simply collecting as they orbit, they're actually tasked. We're tasking every volcano along the Kamchatka Peninsula monthly. And so these elevation models can be laid upon one another and then subtracted. And then you can see where the deforestation is, where also the eruptions are. Next slide. And so here's where Jim's work starts coming into play. Do you want to talk about this?
Okay, thanks, Paul. So one of the really cool things, if you study the carbon cycle, is this is a three-dimensional problem. If you only deal with the carbon cycle in 2 dimensions, you have no idea about volume or biological mass. Because these data are 3-dimensional, you can look at the volume of vegetation which is removed, and that translates into a weight because you have 3 dimensions to work with. So we see here's one image from November of 2012. Here is another image of the same area from June of 2015. And what you notice, all of these rectangular areas are areas where the boreal forest was cut and removed. Eric, the next slide. And so now, when you combine these images, you're actually able to look at volumes of forests which have been removed. And for the carbon cycle, this is massive. This is what we hope to do in tropical and subtropical areas with a combination of Landsat data and LiDAR data or SAR data. With commercial satellite data in the Arctic regions, you can do it directly from data at a 2 meter by 2 meter XY with plus or minus 15 meters in the vertical. This is revolutionary for our study of the carbon cycle. You want to finish up?
And so what you saw before, that you could see the individual trees being removed for the logging roads, but now also this data is accurate enough that we can say that on this part of this clear cut, the trees were 12 meters tall before they were cut, and on the other side, they were 20 meters tall. So it's actually volume at that point. And remember, we're not dealing with a Landsat pixel, which is 15 meters for panchromatic. We're dealing with a high resolution elevation model where the DEM is 2 meters. Next slide. Here's the scary one. This is the Vavilov ice cap. If you go to the center of Siberia, all the way to the top, right before you hit Canada, it's this ice cap. So this ice cap is about 75 or 100 kilometers wide. And what we're going to look at is a time series of this elevation model over a period of about 4 years. So next slide. Here's the next year. And so this is March 2014. You can see a surge beginning here. Next slide. The surge continues. And the next slide. this surge completes. That's sea level rise in action. That's 1/100th of a millimeter of sea level rise per year, just from this one surge. And if you go to the next slide, please. Here's the difference. So we're looking at these surges on a 2 meter by 2 meter pixel, year by year, month by month. Next slide. So if you're doing one end of the planet, you might as well do the other end of the planet at the same time. And so sometime this winter, we'll be releasing an 8-meter resolution elevation model of the entire Antarctic as well, 100,000 DEMs. So now, after the Antarctic is released in about February or so, the Antarctic will have better elevation than we have for the western United States, including California and Colorado. Next slide. That's it? Okay. Okay. So thank you very much.